Crystal field theory is all about the d-orbitals. It is a model which evaluates the properties of complexes that result when d-orbitals split into different energies due to interactions between the metal ion and the ligands. Now, ligands bring with them a lone pair of electrons to form a bond with the metal ion. The lobes of the d-orbitals also represent areas of electron density. So I'll just note that by writing a few electrons in a few locations. When a ligand approaches a metal ion in an octahedral complex, it's actually the electrons that are approaching. And this happens along the axes of the d-orbitals. So the ligand will come in like this, or like this, or like this, just as an example. You can see from the highlighting that there isn't much overlap between the ligand electrons and the electron density of the d-orbitals. Compare that with the other two orbitals where the electron density is on axis. As the ligands approach also on axis, there's a much greater overlap between the electrons of the ligand and the electrons within the d-orbitals, compared to the top three orbitals where there is less overlap. Greater overlap means that there is higher repulsion or greater repulsion because you have like charges. You have negative charges in both locations. The top three experience less repulsion. Greater repulsion results in a higher energy, and lesser repulsion results in a lower energy. What happens is that the d-orbitals will split into two energy levels, with the dx squared minus y squared and dz squared orbitals higher in energy than the dxy, dyz, and dxz. The energy gap between these two sets of orbitals is called the crystal field splitting energy, and we note that as delta. This specific splitting pattern corresponds to an octahedral complex. There are different splitting patterns for the other geometries, and we will not cover them in this class. So there are two types of predictions that we will make with this model based on the splitting of the d-orbitals. The first is related to the paramagnetism of the complex, and the second is related to its color. Both of these predictions are directly related to the magnitude of delta. The spectrochemical series shows us how the ligand in the complex is associated with a higher delta called a stronger field ligand, or a lower delta which corresponds to a weaker field ligand. The dividing line is at thiocyanate. If a ligand is strong field and has a large delta, then there is a larger energy gap between the two sets of d-orbitals in the energy level diagram. A larger delta corresponds to a shorter wavelength of light absorbed. The opposite is true for a smaller delta, which absorbs a longer wavelength of light. The color of light absorbed can be related to the color of the complex through complementary colors, or ROY equals GBV. In terms of electrons, the first three electrons will fill into the first three orbitals as unpaired electrons, regardless of which ligand is attached. Where the fourth electron goes depends on delta. For strong field ligands, the fourth electron will enter the lower energy level paired because the pairing energy is less than delta, or is smaller than delta. This leads to the minimum number of unpaired electrons, called a low-spin complex, which is less paramagnetic. For weak field ligands, the fourth electron will enter the higher energy level unpaired, because the pairing energy is greater than delta. This leads to the maximum number of unpaired electrons, called a high-spin complex, which is more paramagnetic. In our first example, we have a chromium complex, and we are asked to fill in the electrons into the d orbitals and count the unpaired electrons. So the first thing that we notice is what type of a complex we have. And what I mean by that is whether the ligand is a strong field ligand or a weak field ligand. Hydroxide is considered a weak field ligand. We might need to use that information. The other thing we need to know is what is the charge on the metal ion, because that will determine how many d-electrons we have. We'll count the d-electrons later, but for right now, let's just determine the charge on the chromium. So my chromium has a charge of X plus 6 times hydroxides, which have a -1, and that needs to equal the charge on the complex, which is a -4. So X equals +2. So my metal ion is chromium 2. The next thing I'll do is sketch my energy level diagram with my split orbitals. The top orbitals are my dx squared minus y squared and my dz squared. It doesn't matter in which order you write these because these two orbitals are degenerate. Degenerate is a fancy way of saying that they have the same energy. So I can write them in either order. For my lower 3 orbitals, they are also degenerate with one another. So my dxy, dxz, and dyz can be written in any order. The next thing I need to do is figure out how many d-electrons I have to work with. So I'm going to write a regular orbital diagram, one where the metal is not in a ligand field. So I'm going to start with chromium, neutral chromium, and write the noble gas version of this. So sketching out my orbitals, I have my 4s orbitals and my 3d orbitals. For neutral chromium, the orbital diagram is 4s1, 3d5. You might remember that chromium is an exception and all of the orbitals are half filled. To form the ion, which I determined is a 2+, I need to remove 2 electrons. So the first one is this 4s, and the second one is the last d. This gives me a d4 structure. So I have 4 electrons to work with to fill into my split orbitals. When I start to fill electrons, I fill the first 3 as single unpaired electrons. The 4th electron, where it goes, depends on whether you have a strong field or a weak field ligand. I have a weak field ligand, which means that this energy gap, delta, is small. Because delta is small, then that means the 4th electron can fill up here as an unpaired electron. And when I go to count my unpaired electrons, I have 4 unpaired electrons. My next example is similar. I need to write and fill in the orbital diagram for a different complex. This one has ammonia ligands, and ammonia is considered a strong field ligand. I need to check the charge on my metal ion. I have X for the chromium plus 6 times 0 equals a +2, or X equals a +2. So I have the same metal ion as I did in the last example. That means, lucky for me, that I don't have to sketch out the orbital diagram again, the first one, because I already figured out that I have 4 d-electrons to work with. I do need to write my split orbitals and label them. So I have my dx squared minus y squared and dz squared as my top 2. And I'm just going to exaggerate this distance here because it's a large delta. So I have my dxy, dyz, and dxz. This is a large value of delta. When I go to fill in my 4 electrons, my first 3 always fill in like this, and the 4th one depends on the magnitude of delta. Since this is a large delta, it means it's more difficult for that 4th electron to go way up to the top energy level, and so it will fill in as a paired electron in the lower energy level. And so in this example, I have 2 unpaired electrons. So our next question is asking which complex is more paramagnetic. In order to determine that, in order to compare 2 complexes and determine which one is more or less paramagnetic, you must know how many unpaired electrons there are. Usually that means filling the electrons into the orbital diagrams like we just did. Alternatively, you might be actually given the number of unpaired electrons, and you can determine from that. These are the same 2 complexes that we had in our previous examples. So we have already figured out how many unpaired electrons we have. The first complex had 4 unpaired electrons, and the second complex had 2. More paramagnetic means a higher number. And so the more paramagnetic complex is this one. And our last example has us comparing 2 complexes again. We're told the colors of the 2 complexes, and we need to identify the color of each one. Color is always related to delta. So the first thing that we're going to do is figure out the relative magnitude of delta. Which one has larger energy gap versus smaller energy gap? Ethylene diamine is a strong field ligand, so its delta is larger than the complex with bromine. So that's the first thing I have to figure out. From there, I go through my arguments about energy and wavelength in terms of what is absorbed. So my ethylene diamine complex has a larger delta, which means a larger energy. Larger energy corresponds with absorbing shorter wavelengths. And when I look at the bromine complex, I have a smaller energy and a longer wavelength. So for the moment, I'm going to stop there, and I'm going to switch my line of reasoning to the colors of the complex. So my green complex, I know if it looks green, it absorbs red in terms of the light. The orange complex will absorb blue light. And I can make those predictions fairly easily through my complementary colors and how they're related. So red is related to green, orange to blue, and yellow to violet. So you can connect color of light absorbed with color that the complex looks. The next thing I'm going to do is relate these colors of light absorbed to their wavelengths. So red light versus blue light, red light has a longer wavelength and blue light has a shorter wavelength. And now I can link my 2 trains of thought. So the green complex has to be the one with the bromide ligand, because those both, we determined, had the longer wavelength of light absorbed, and the orange complex corresponds to the shorter wavelength absorbed. And so my ethylene diamine complex is orange, and the bromide complex is green.